Section 4.4, Tangent Planes and Linear Approximations. In Calc 1, we found tangent lines to surfaces using derivatives of our curve. But what about a tangent plane? How do we find the slope or the perpendicular vector we need for the plane? That's what we're going to talk about. So the first thing I want to do is think about a tangent line to a 3D surface. If we were to try and draw some tangent lines through this point to the surface, we might each draw something a little bit different. In fact, there are infinitely many tangent lines to the surface that pass through this point. And because there's infinitely many, we can contain them all in a plane, and that plane containing all of the infinite tangent lines, that's called the tangent plane. To find the tangent plane, we'll use the equation that I have posted up on the screen. It has a few separate components to it. One of them is a point on the surface. Second part of this equation is the partial of our function with respect to x. So the partial with respect to x, partial derivative. And then we're multiplying by the change in x relative to a fixed starting point, so that x0 starting point. And then we also have our partial with respect to y. Multiplied by our change in y. Each of these partials is evaluated at that point, x0, y0, so we'll make sure to do that. Now looking at this equation, you might question, is that really tangent to our surface? That's a great habit to get into. We should always ask these types of questions. So is that plane that we see at the top of the screen really tangent to our surface? Well, let's try and convince ourselves visually. If I have a surface like the blue one that I have plotted with the white dot, the point A on the surface, we can start off by intersecting our surface with a plane x equals a constant. And we see that here, and then inside of that plane, let's find the tangent line. So this reduces down to a Calc 1 problem. And then we can do the same thing in the y direction, slicing our surface with a plane y equals a constant. Then we can find the curve that intersects our surface and that plane, find the equation of the tangent line, just like we did on our partial derivatives. If we keep just both of the tangent lines here, we can see that they're contained in the same plane that I have plotted on the surface. But we want to convince ourselves whether or not that plane that we have drawn here is the same as the plane that we get from the equation at the top of the page. So to do that, let's focus on the fact that we have the two tangent lines in our graph. The lime green tangent line came from the y partial. And if we wanted to come up with an equation for a vector that's parallel to this line, remember slopes in 3D, we usually use vectors rather than rise over run, but in this case we're going to kind of use both. So a vector parallel to this line should have no change in the x direction, and that's because we sliced the plane x equals a constant into our surface, which means x is fixed, it's not allowed to change anymore. And then in the y and x components, y and z components, we're kind of creating a slope in the yz plane, just like we would have in the xy plane, where the partial derivative, or the derivative with respect to y, is our slope, which would be rise over run. In the yz plane, z is the value that rises, so fy, the partial with respect to y, is our rise. And we're going to look at this as a unit slope, so we're running in the y direction 1. So we have 1 in the y direction, our derivative in the z direction. If we look at the equation of the other tangent line, so the pink tangent line, we essentially have the same thing. If we wanted to find a vector parallel to this line, we can tell that there would be no change in the y direction. And again, that's because of the plane that we sliced our surface with. And then our slope is in the xz plane. That partial derivative with respect to x is essentially our rise over run. We're running in the x direction, rising in the z direction. So we plug those in here. Now that we have these two vectors, we can cross them and we can find a vector that's perpendicular to each one of them. And if we find a vector that's perpendicular to each one of those tangent lines, then that vector is going to be perpendicular to the plane that contains all of those tangent lines. Which means we can use that vector, that perpendicular vector, to define our tangent plane. So let's go ahead and calculate that cross product. I've copied the vectors over from the previous slide and I've named them. So we have A and B, and we're crossing them. So we'll do our I hat, J hat, K hat. We'll fill in the A vector for our second row. Instead of writing f with respect to y evaluated at x0, y0, for this calculation, I'm going to simplify the notation and just write the partial with respect to y. And then when we go back to compare, we will write out the full notation. And same with our b vector. When I plug in my b vector in the bottom row, I have 1, 0, and then my f partial with respect to x. I'm not going to write that I'm plugging in points because it just makes the notation too cumbersome. We'll go back to that in a minute. So I'll do my I hat, and then that would be times the f partial times 1 minus the y partial times 0, which just leaves me with I hat times our f with respect to x partial, minus our j hat times 0 f partial with respect to x, minus 1 times f partial with respect to y, so that would look like minus f partial with respect to y, and then plus our k hat, which would be 0 times 0 minus 1 times 1, which would just be minus 1. And we can simplify this writing it in our bracket notation. In the x component, we have the f partial with respect to x. In the y component, we have the f partial with respect to y. In the z component, we have a -1. And because I did get a little bit lazy on notation, let's go back and rewrite that we're actually evaluating each of these partials at x0, y0. Cool, we did our cross product. Now let's remember the equation of a plane. It needs a perpendicular vector like A, B, C, and then it needs a point on the plane like x0, y0, z0. And then if we have those two things, we can plug them into the scalar equation, which would look like A times x minus x0 plus B times y minus y0 plus C times z minus z0, and that's equal to 1. So let's plug in all we've got. The perpendicular vector is what we have in purple over here, where the f partial with respect to x, evaluated at x0, y0, that's our A. F partial with respect to y, evaluated at our point, is B, and then -1 is c. So let's go ahead and plug those into our equation of the plane. And then let's go back and compare it to everything that we have in the equation of the plane at the top of the screen. So I see the f partial with respect to x evaluated at our point multiplied by the change in x. That matches exactly what we have right here. Awesome. And let's match up anything else. How about the f partial with respect to y times the change in y? That matches up right here. Perfect. But not everything matches. We have z and z0 here, and the equation of the plane up here just has a z, no z0. But if f is a function of x and y, it produces z values. So if I plug x0 and y0 into f, it'll produce z0. So when I have z0 written over here in our calculation, that's really the same thing as f evaluated at x0, y0. So when we distribute our -1 on that last term and rearrange our equation, we do get exactly the same thing as the equation at the top of the slide. Z equals f at x0, y0 plus f partial with respect to x evaluated at that same point multiplied by the change in x plus our y partial evaluated at our point multiplied by the change in y. Cool, so hopefully we're convinced that this equation does truly give us the tangent plane to a surface f at a point x0, y0. Let's go ahead and practice using this. If we want to find a tangent plane for a surface like f of xy equals all the stuff you see right there on the screen. I don't want to read it all out. 2x squared minus 3xy plus xy squared plus 2x minus 4y plus 4. There, I did it. We need to do three things. First, let's evaluate our function at the point where we're looking for the tangent plane. So our point is going to use x0 as 2, y0 as -1. So we're really looking for f at 2, -1. If we plug that into our function and simplify it out, should get 34. Let's move on to the next calculation, the f partial with respect to x. We'll first take the partial, then we'll evaluate it at x0, y0. Remember, when you take the partial derivative with respect to x, you treat y as if it's constant. So any term that depends only on y is treated just like a constant. The derivative would be 0. But any term that has an x in it, we will take the derivative just like in Calc 1. So 2x squared becomes 4x, -3xy becomes -3y, and 2x becomes 2. And then we evaluate that at the point x0, y0. In other words, we're going to evaluate our partial at 2, -1. And we get 13. Now we can move on to find the partial with respect to y. When we do the partial with respect to y, we treat x as if it's constant. So any term that depends completely on x or is a constant would go to 0 when we take the derivative. But the negative 3xy becomes negative 3x. The 8y squared becomes 16y. And the minus 4y becomes minus 4. And then we'll evaluate that at 2, negative 1 as well. To get negative 26. Lastly, we can plug all of these values into the equation at the top of the slide. So we'll have z equals f at x0, y0 was 34, plus our partial with respect to x, evaluated at our point, was 13. Then we multiply by the change in x using x0 as 2. Then add the partial with respect to y, evaluated at our point, that was negative 26. Multiply that by our change in y, where y was negative 1. And then we can clean this up a little bit. Distribute our 13 into the parentheses, distribute our negative 26 into the parentheses. Oops, that should be minus 26 at the end, not plus. We'll combine our like terms. For our final answer, z equals 13x minus 26y minus 18. I would encourage you to hop on to GeoGebra and plot this to make sure that you see it really does generate a tangent plane. So plot your surface. Plot the point on the surface. Remember, you're given the x and the y, but you have to calculate the z. And then lastly, plot the plane, the one that we just found. And you can check visually that you did this problem correctly. The second half of this section has to do with linear approximations. I'll make a separate video for that one. For now, go ahead and work on calculating tangent planes. The first half of your homework assignment, it does ask you to calculate tangent planes for different surfaces. So go ahead and get that started and wait for the next video.